The observable universe at its largest scale appears as a continuous expansion of space itself, a quiet and persistent stretching that defines every distance within it. On this scale, galaxies are not simply moving through a static void, but are carried apart by the expansion of space, a behavior described in cosmology as the metric expansion of the universe. The fabric of space is not a material substance, yet it behaves in a measurable way, increasing the separation between distant structures over time. This expansion does not act like an explosion from a single center. Instead, it occurs everywhere at once, affecting all regions beyond the scale where gravity can hold structures together. At the largest distances, the universe becomes dominated by this expansion field. Galaxies appear distributed across an immense three-dimensional structure, and the space between them grows continuously. Light traveling across this environment must traverse regions that are themselves stretching, which means the distance covered increases even during the journey. This effect shapes the observable horizon, limiting how far information can reach any observer within a finite age of the universe. The expansion is subtle on small scales but becomes dominant at intergalactic distances. Within gravitationally bound systems such as galaxies or clusters of galaxies, the local forces overcome expansion, maintaining stable structures. Beyond these regions, however, expansion becomes the primary influence. Space itself increases the separation between galaxy systems, and this process continues without a known endpoint in current cosmological models. On the larger scale, matter is arranged in a pattern that reflects both initial conditions from the early universe and the ongoing influence of expansion. The density of matter is extremely low when averaged across vast volumes. Galaxies occupy only a tiny fraction of space, while the rest is filled with extremely thin gas and near-perfect vacuum. The result is a universe that is structured yet overwhelmingly empty in most regions. The expansion field is not uniform in its effects on perception. To local observers, nearby galaxies may appear stable, bound, and structured, but as distance increases, the rate at which separation grows becomes more pronounced. This leads to a transition where the motion of galaxies is no longer dominated by local gravity, but by the stretching of space itself. This transition defines the boundary between local cosmic structures and the large-scale flow of the universe. The observable universe is defined by the distance light has been able to travel since the beginning of cosmic expansion. This boundary is not a physical wall, but a horizon shaped by time and the finite speed of light. Regions beyond this horizon remain unseen not because they do not exist, but because their light has not yet reached the present point of observation. As expansion continues, some regions move beyond this horizon, becoming permanently unobservable in practice. The large-scale expansion also influences how matter is distributed. Over time, dense regions become more isolated from one another. Galaxy clusters remain as gravitational islands, while the space between them grows increasingly empty. This separation enhances the impression of vastness, as structures that were once closer become more remote over cosmic timescales. Even though the expansion is gentle on local scales, its cumulative effect across billions of years produces extreme separations. Distances that were once small in the early universe become immense as space stretches continuously. The universe does not require movement through space for this separation to increase. Instead, space itself changes, altering the distances between fixed points defined by large-scale structures. This behavior creates a fundamental characteristic of cosmic structure. Isolation increases with scale. The larger the distance between two galaxies, the more strongly expansion dominates their relationship. At extreme scales, galaxies become effectively separated by regions that expand faster than light can bridge through normal travel. This does not violate physical laws, as it is space itself that expands rather than objects moving through space at high speed. The observable universe therefore exists as a balance between expansion and structure. Gravity shapes local systems, while expansion shapes the large-scale arrangement of everything beyond them. The interplay between these two influences defines the cosmic landscape, producing a universe that is both structured and increasingly empty as scale increases. Within this expanding framework, distances gain a dynamic quality. They are not fixed measurements, but evolving quantities shaped by the history of cosmic expansion. Every region of space carries a record of this expansion. In the way light is stretched, matter is distributed, and structures are separated over time. The result is a universe where distance itself becomes an active feature of cosmic behavior. It is not merely the space between objects, but a changing property of the universe growing steadily and silently across all large scales. This fundamental expansion establishes the foundation for understanding why the separation between galaxies becomes so extreme, and why the universe appears increasingly isolated as it evolves. At a deeper level within the large-scale structure of the universe, matter is not distributed randomly, but arranged into vast interconnected formations known as the cosmic web. This structure emerges from the subtle interplay between gravity and the expansion of space shaped over billions of years from tiny fluctuations in the early universe. The cosmic web defines the scaffolding on which galaxies form, yet it also reveals how most of the universe is not filled with galaxies at all, but with long stretches of near-empty space. These structures take the form of filaments, which are elongated regions, where galaxies and gas are more densely concentrated. Filaments stretch across hundreds of millions of light-years, connecting massive clusters of galaxies like faint threads in a vast three-dimensional network. Within these filaments, matter slowly flows under the influence of gravity, gradually collecting into denser nodes where galaxy clusters form. The filaments themselves are not solid structures, but regions of slightly higher density guiding the movement of matter across cosmic time. Between these filaments lie enormous regions where matter is extremely sparse. These spaces are known as cosmic voids. A void is not completely empty, but its density is so low that it contains very few galaxies compared to the filaments surrounding it. In many cases, a void may span tens or even hundreds of millions of light-years, with only a handful of isolated galaxies drifting within it. These regions define the true emptiness of the universe on large scales, where the absence of matter becomes a dominant feature of cosmic structure. The cosmic web forms as a result of small density variations in the early universe. Over time, gravity amplifies these variations, pulling matter into regions that are slightly denser than their surroundings. As matter flows inward, voids become emptier, while filaments become more pronounced. This process continues over billions of years, gradually sharpening the contrast between dense structures and empty regions. The universe evolves into a pattern where most matter is confined to narrow channels, leaving vast volumes of space almost entirely devoid of galaxies. Within this network, galaxies do not move randomly, but follow the underlying structure shaped by gravity. They drift along filaments, slowly converging toward clusters where gravitational attraction is strongest. This movement occurs over extremely long timescales and is influenced by both local gravity and the overall expansion of space. Even as galaxies move along these filaments, the expansion of the universe continues to stretch the filaments themselves, maintaining the vast separation between structures. The emptiness of voids is not simply a lack of galaxies, but a fundamental aspect of cosmic evolution. As matter is drawn into denser regions, voids expand and become even less populated. Over time, they grow larger and more isolated, forming some of the most extreme low-density environments known in the universe. Light traveling through these regions encounters very little matter, allowing photons to pass through vast distances with minimal interaction. Despite their emptiness, voids are not entirely uniform. Subtle variations in density still exist within them, and faint structures of gas and dark matter can be present. However, these are so diffuse that they do not form galaxies or significant luminous objects. Instead, they remain part of the invisible framework that continues to evolve under the influence of gravity and expansion. The contrast between filaments and voids creates a universe that is highly structured on one scale, yet profoundly empty on another. From a distance, the cosmic web resembles a delicate network, but as scale increases, the emptiness between its threads becomes more dominant. This contrast is essential to understanding why the universe appears both connected and isolated at the same time. As cosmic expansion continues, the separation between filaments grows, and voids become even more prominent. Structures that were once relatively close drift further apart, reinforcing the sense of increasing isolation. The cosmic web does not dissolve, but its components become more widely separated, making the universe appear increasingly sparse over time. The existence of this web-like structure highlights a key feature of cosmic evolution. Matter is not evenly distributed, and most of space contains very little material. Galaxies, despite being numerous on human scales, occupy only a small fraction of the total volume of the universe. The rest is dominated by vast empty regions shaped by the ongoing competition between gravity pulling matter together and expansion pulling space apart. Within this balance, the cosmic web serves as both a map of structure and a record of emptiness. It shows where matter has gathered, but also where it has been left behind. The spaces between filaments are not secondary features, but central to the overall architecture of the universe. They define the scale of separation between galaxies and establish the true sense of cosmic distance that grows more extreme as the universe evolves. On the largest gravitational scales within the cosmic web, matter gathers into immense structures known as superclusters and galaxy clusters, forming the most massive bound systems in the universe. These structures represent regions where gravity has succeeded in collecting vast numbers of galaxies into shared environments despite the ongoing expansion of space. A galaxy cluster contains hundreds to thousands of galaxies bound together by mutual gravitational attraction, while superclusters are even larger associations that link multiple clusters into loosely connected groupings. Within these regions, gravity acts as the dominant force over local scales, maintaining coherence against the background of cosmic expansion. Galaxies within a cluster orbit a common center of mass, often dominated by dark matter, an invisible form of matter inferred from gravitational effects. Dark matter does not emit light, yet it provides the majority of the gravitational framework that holds clusters together. Its presence allows clusters to remain intact, even as the universe continues to expand on larger scales. Superclusters, however, are not always fully bound systems. Many of them are only partially gravitationally connected, meaning that different clusters within a supercluster may not remain permanently bound over cosmic time. As expansion continues, some of these large structures gradually stretch apart, revealing that even the largest known groupings of galaxies are not immune to the effects of an expanding universe. The scale of separation between clusters is immense. Distances between individual clusters can span tens of millions of light years, and between superclusters the gaps can become even larger. These distances are not static, as the expansion of space slowly increases the separation between structures that are not strongly bound by gravity. Over time, this process leads to a gradual isolation of clusters, Even within regions that once formed part of larger cosmic systems, inside clusters galaxies exist in relatively close proximity compared to intergalactic scales. They interact gravitationally, occasionally passing near each other or merging over long periods. These interactions can reshape galaxies, triggering bursts of star formation or altering their structure. Despite this activity, the space between individual galaxies within a cluster remains largely empty, filled with hot gas and dark matter rather than dense matter. The intracluster medium, a diffuse plasma filling the space between galaxies and clusters, plays a significant role in the evolution of these systems. This hot gas is heated to extremely high temperatures by gravitational processes emitting X-rays that can be observed by space telescopes. Although it is extremely thin compared to air on Earth, it still represents a measurable component of the cluster environment. Beyond clusters, the transition to intercluster space reveals a dramatic drop in density. The relatively structured environment inside clusters gives way to vast regions where galaxies are much more widely separated. In these regions, gravitational interactions between individual galaxies become rare, and expansion begins to dominate the large-scale motion of structures. Superclusters are often described as the largest coherent structures in the universe, yet even they exist within a larger context shaped by cosmic expansion. Some superclusters are connected by faint filaments of the cosmic web, while others appear as isolated groupings slowly drifting apart. Over extremely long timescales, expansion may reduce the connectivity between these systems, further increasing the sense of cosmic separation. The distribution of matter within these structures reflects both the initial conditions of the early universe and the ongoing influence of gravity and expansion. Regions that began with slightly higher density evolved into clusters and superclusters, while surrounding areas became increasingly empty. This uneven distribution is a fundamental feature of cosmic structure, not a temporary state. As light travels across these vast regions, it carries information about the separation between structures. The longer the distance, the more the expansion of space affects the properties of that light, stretching its wavelength and reducing its energy. This effect encodes the history of cosmic expansion into the light itself, allowing observations to reveal the scale of separation between distant structures. Even within these massive systems, the universe remains predominantly empty. The galaxies that form clusters and superclusters occupy only a tiny fraction of the total volume. Most of the space within and between these structures is filled with extremely low-density matter, or remains nearly empty on a scale that challenges direct visualization. The existence of clusters and superclusters demonstrates that gravity can create order within an expanding universe, but it also highlights the limits of that order. Beyond certain scales, expansion becomes dominant and structures begin to separate from one another. This balance between binding and expansion defines the architecture of the universe and sets the stage for even greater isolation at larger distances. At even larger scales, the universe reveals regions where matter becomes so sparsely distributed that structure itself appears to dissolve into near-total emptiness. These regions are known as cosmic voids at their most extreme scale, where entire volumes of space contain almost no luminous matter. In these vast expanses, galaxies are rare, and when present they are often small, isolated, and far from any significant gravitational neighbours. The emptiness is not absolute yet. It approaches a level where matter becomes a negligible presence compared to the volume of space. These extreme voids emerge naturally from the evolution of the cosmic web. As gravity pulls matter into filaments and clusters, surrounding regions lose material and expand into increasingly empty spaces. Over billions of years, this process intensifies, leaving behind enormous cavities in the distribution of galaxies. These voids are not static holes, but evolving regions where the density continues to decrease, relative to the cosmic average, as matter flows outward toward denser structures. Within these voids, the intergalactic medium becomes even thinner than in filament regions. The intergalactic medium is the sparse gas that fills space between galaxies, primarily hydrogen and helium left over from the early universe. In voids, this gas exists at extremely low densities, often so thin that interactions between particles are rare over vast timescales. Despite its faint presence, it still traces the underlying structure of dark matter, which continues to influence the shape of space even where visible matter is nearly absent. Light passing through these regions experiences minimal obstruction. Photons can travel across enormous distances without encountering significant matter, preserving much of their original information. However, the expansion of space still affects them, stretching their wavelengths and gradually shifting their energy. Even in the emptiest regions, the influence of cosmic expansion remains constant, ensuring that distance continues to grow regardless of local density. The contrast between voids and surrounding filaments becomes more pronounced at this scale. Filaments appear as narrow, luminous threads of galaxies and gas, while voids expand into vast dark volumes that dominate the total space of the universe. From a volumetric perspective, voids occupy most of the universe's space even though they contain very little mass. This imbalance between volume and matter is a defining feature of cosmic structure. Inside these voids, gravitational interactions are weak due to the scarcity of nearby mass. Galaxies that exist within voids are often referred to as field galaxies, and they tend to evolve in relative isolation. Without frequent interactions or mergers, their evolution follows a slower and more solitary path compared to galaxies and clusters. Star formation within these galaxies can be influenced by internal processes rather than external gravitational disturbances. Despite their emptiness, voids are not uniform. Subtle variations in density exist, and faint filaments of gas and dark matter can still pass through them. These faint structures act as remnants of the larger cosmic web, showing that voids are not truly separate from the rest of the universe, but are part of a continuous network shaped by gravity and expansion. The evolution of voids is closely tied to the acceleration of cosmic expansion. As expansion continues, voids tend to grow larger, because regions of lower density experience less gravitational resistance. Over time, this leads to an increasing separation between matter-rich regions, making voids more prominent features of the cosmic landscape. This growth contributes to the overall impression of increasing emptiness on the larger scales. The boundaries between voids and filaments are not sharp but gradual. Density changes smoothly across space, creating transitions rather than rigid edges. This continuity reflects the underlying physics of gravitational collapse and expansion, where matter flows continuously, rather than forming strict boundaries. As a result, the structure of the universe appears as a gradient of density rather than a set of discrete regions. On the larger scales, the universe becomes increasingly dominated by these void regions. Although galaxies remain numerous in absolute terms, their distribution across vast volumes creates an impression of extreme isolation. Each galaxy becomes separated from others by distances that are difficult to comprehend, with large stretches of space containing little more than thin gas and dark matter. This increasing emptiness is not a sign of decay but a natural outcome of cosmic evolution. The initial conditions of the universe contained small fluctuations in density, and over time these fluctuations were amplified by gravity and expansion. The result is a universe where matter is concentrated into a small fraction of space, while most of the volume becomes increasingly empty. The extreme scale of these voids highlights the central theme of cosmic distance separation grows not only between galaxies but within the very structure of space itself. As voids expand and filaments thin, the universe becomes a place where distance dominates structure, shaping everything from the movement of galaxies to the path of light across billions of years. Within the vast intergalactic medium that fills the space between galaxies, matter exists in one of its most diffuse and extended forms. This medium is composed primarily of hydrogen and helium, left over from the early universe spread so thinly that individual atoms are separated by enormous distances. Although it is often described as a vacuum on human scales, it still contains a measurable presence of particles that trace the underlying structure of the cosmos. This medium occupies the space between filaments, clusters, and voids, forming a faint background environment that extends across intergalactic space. The density of this gas is extremely low, far below any conditions naturally found within galaxies. In many regions, a single atom may occupy volumes of space that span many meters or more on average separation scales, making interactions between particles extremely rare. Despite this, the intergalactic medium plays a critical role in cosmic evolution, as it carries the residual material from galaxy formation and provides a reservoir of gas that can, under the right conditions, fall into galaxies and contribute to future star formation. This medium is not uniform. In regions closer to filaments and clusters, the gas becomes slightly denser and hotter due to gravitational compression and energetic processes. In contrast, within deep voids, it becomes colder and more rarefied. These variations are subtle but significant on cosmic scales, shaping the way matter flows through the universe over billions of years. The structure of this medium reflects the invisible influence of dark matter, which organizes the large-scale distribution of baryonic gas. Dark matter itself does not interact with light, but its gravitational presence shapes the pathways along which visible matter moves. The intergalactic medium follows these gravitational contours, gradually collecting along filaments and thinning within voids. Over time, this results in a highly structured yet extremely diffuse network of gas that spans the universe. Even though the gas is nearly invisible, it can be detected through its interaction with distant light sources, particularly through subtle absorption features in the spectra of quasars. As light from distant objects passes through the intergalactic medium, it interacts with the sparse hydrogen atoms along its path. These interactions leave faint signatures that reveal the presence of otherwise invisible matter. Over immense distances, these signatures accumulate, allowing astronomers to map the distribution of gas across the universe. This method reveals that even the emptiest regions are not entirely void, but contain traces of matter distributed in delicate patterns. The temperature of the intergalactic medium varies depending on its environment. In some regions, it's heated by shocks from collapsing structures, reaching temperatures of millions of degrees. In these hot phases, the gas becomes ionized, meaning electrons are separated from nuclei, forming a plasma state. In other regions, particularly within voids, the gas remains cooler and less energetic, though still extremely diffuse compared to galactic environments. The movement of this gas is governed by both gravity and the expansion of space. Gravity draws it toward denser regions, while expansion stretches the overall framework of the universe, increasing the separation between structures. This dual influence creates a slow, continuous flow of matter across cosmic time, with gas gradually migrating along filaments toward clusters where galaxies reside. Despite its faintness, the intergalactic medium contains most of the ordinary matter in the universe. While galaxies contain concentrated regions of stars, planets, and dense gas, the majority of baryonic matter is distributed in this thin, extended state. This fact highlights the hidden nature of cosmic structure, where most matter is not visible in traditional forms, but exists in diffuse, nearly transparent environments. The interplay between the intergalactic medium and cosmic expansion contributes to the growing sense of emptiness on large scales. As space expands, the density of this gas decreases further, spreading it over increasingly larger volumes. This process enhances the separation between regions of higher density, reinforcing the isolation of galaxies and clusters. Even though the intergalactic medium is extremely thin, it forms a continuous bridge across the universe. It connects regions separated by vast distances, ensuring that matter is never entirely isolated, even in the most remote voids. This continuity reflects the underlying unity of the cosmic web, where all structures are linked through gravity and shared origin. Over time, however, this connectivity becomes less influential as expansion increases separation. The gas becomes more diluted, and its ability to form new structures diminishes. Yet it continues to trace the architecture of the universe, preserving a faint record of cosmic evolution. The intergalactic medium therefore represents both connection and isolation at once. It is a medium that fills the space between galaxies while simultaneously emphasizing how little matter exists compared to the vastness of space itself. Its extreme thinness highlights the central theme of cosmic distance. Even where matter exists, it is stretched across such immense scales that separation dominates structure. Within the large-scale structure of the universe, one of the most influential forces shaping separation between galaxies is the phenomenon of cosmic expansion driven by dark energy. Dark energy is a term used to describe the observed acceleration in the expansion of space, a behavior measured through distant supernova and large-scale galaxy surveys. It does not behave like ordinary matter or radiation, and its physical nature remains unknown. What is established through observation is its uniform presence across space and its dominant role in the evolution of cosmic expansion on the larger scales. As space expands, the distance between unbound galaxies increases over time. This expansion is not caused by galaxies moving through space in a conventional sense, but by the stretching of space itself. Dark energy influences this process by increasing the rate at which expansion occurs. Over billions of years, this effect becomes more pronounced, leading to a universe where distant structures separate from one another at an accelerating pace. The influence of dark energy is not uniform across all scales in terms of perceived impact. Within gravitationally bound systems such as galaxies or clusters of galaxies, local gravity is strong enough to resist the effect of expansion. Stars within galaxies remain stable and galaxies within clusters remain bound. However, beyond these regions, dark energy becomes the dominant factor, gradually increasing the separation between independent structures. This accelerating expansion means that galaxies not gravitationally bound to each other will drift apart at increasing rates. Over long timescales, this leads to a situation where distant galaxies move beyond observable reach. Their light becomes stretched and weakened, and eventually it may no longer be detectable by observers within a given region of space. This process contributes to the gradual isolation of cosmic structures. The effect of dark energy is subtle on small scales, but becomes significant when distances are measured across billions of light years. In these regimes, the expansion of space is no longer constant but accelerating. This acceleration changes the long-term geometry of the universe, shaping its future evolution. Current observations suggest that this accelerated expansion has been occurring for several billion years, gradually becoming the dominant influence over cosmic dynamics. The presence of dark energy also affects the structure of the cosmic web indirectly. As expansion accelerates, the growth of large-scale structures slows down. Filaments and clusters that formed earlier in cosmic history continue to exist, but new large-scale connections become increasingly difficult to form. Over time, this leads to a frozen structure where existing formations persist, while new large-scale organization becomes limited. On the scale of galaxy clusters, dark energy has little immediate effect. Gravity within clusters remains strong enough to maintain cohesion. However, between clusters, expansion continues to increase separation. This creates a layered universe where some structures remain stable, while others drift apart at accelerating rates. The contrast between bound and unbound regions becomes more pronounced as time progresses. The concept of an accelerating universe also influences the observable horizon. As expansion accelerates, there are regions of space that move beyond the ability of light to reach an observer. This means that parts of the universe that are currently visible may eventually become unobservable. Conversely, light emitted today from distant regions may never reach certain observers if expansion carries these regions away too quickly. Dark energy does not appear to cluster or concentrate in any known way. It is observed to be uniformly distributed across space, acting consistently regardless of location. This uniformity suggests that its influence is tied to the geometry of space itself, rather than to localized sources. As space expands, the total effect of dark energy increases because more space exists for it to act upon. The long-term consequence of this accelerated expansion is a universe that becomes increasingly isolated. Galaxies outside local gravitational systems gradually recede beyond reachable distances. Over extremely long timescales, only bound structures remain visible to each other while distant regions fade from observable contact. This leads to a cosmic environment where separation is not only spatial, but also informational, as signals from distant regions become unreachable. Even though dark energy is not directly observed in a conventional sense, its presence is inferred through precise measurements of cosmic expansion. Observations of distant supernovae show that they are dimmer than expected in a decelerating universe, indicating that expansion has been accelerating over time. Additional evidence comes from the large-scale distribution of galaxies and the structure of the cosmic microwave background, all of which support a consistent model of accelerated expansion. This accelerating expansion contributes to the fundamental sense of distance in the universe. It ensures that separation is not static but increasing at a growing rate. The further apart two unbound regions are, the faster they move away from each other due to expansion. This relationship intensifies the perception of vast emptiness between galaxies. Dark energy therefore acts as a long-term driver of cosmic isolation. It does not create structure, but it shapes the environment in which structure exists. By accelerating expansion, it gradually increases the distances between galaxies, reinforcing the emptiness of intergalactic space, and deepening the separation that defines the large-scale universe. On cosmological scales, the motion of galaxies is deeply influenced by the expansion of space itself, a behavior often described through the Hubble flow. This flow refers to the observation that galaxies, when viewed at sufficiently large distances, appear to be receding from each other at speeds proportional to their separation. The greater the distance between two unbound regions of space, the faster that distance increases over time. This relationship is not caused by galaxies moving through space in a conventional sense, but by the expansion of space carrying them apart. The Hubble flow is most clearly observed when examining distant galaxies whose light has travelled for billions of years before reaching an observer. These galaxies exhibit systematic shifts in the wavelength of their light known as redshift, which indicates that the space between source and observer has expanded during the light's journey. Redshift is not simply a Doppler effect from motion through space, but a direct signature of expanding space, stretching the wavelength of photons as they travel. As light travels through expanding space, its wavelength increases gradually. This stretching reduces the energy of the light and shifts it toward longer, redder wavelengths. Over vast distances, this effect becomes so pronounced that visible light can be shifted into infrared or even longer wavelengths. This transformation encodes a record of cosmic expansion, allowing observations of distant galaxies to reveal how space has changed over time. The Hubble flow becomes more dominant as distance increases. Within local gravitational systems such as galaxies or galaxy clusters, this flow is not noticeable because gravitational forces bind these systems together. Stars within a galaxy do not participate in cosmic expansion, and galaxies within clusters remain gravitationally bound despite the overall expansion of the universe. However, beyond these scales, the Hubble flow becomes the primary factor governing separation. This flow reveals a key aspect of cosmic structure. There is no central point of expansion. Instead, every region of space participates in the expansion equally. From any galaxy, distant galaxies appear to recede, giving the impression that each observer is at the center of expansion. This is a consequence of the uniform expansion of space itself rather than a central explosion. The rate of expansion is described by the Hubble parameter, which quantifies how quickly distances increase with scale. Although this rate changes over cosmic time, it provides a consistent framework for understanding large-scale motion in the universe. Observations indicate that the expansion rate has evolved, influenced in part by dark energy, but the overall structure of the Hubble flow remains a fundamental feature of cosmology. At extremely large distances, the Hubble flow can lead to apparent recession speeds that exceed the speed of light. This does not violate physical laws because it is not motion through space that exceeds this limit, but the expansion of space itself. Light emitted from such distant regions may still travel locally at the speed of light, but the space it moves through expands in such a way that the overall separation increases faster than the light can bridge. This effect contributes directly to the growing isolation of galaxies. As expansion accelerates, more regions of the universe cross thresholds beyond which their light can never reach a given observer. These regions effectively leave the observable universe over time, not because they disappear, but because their connection through light becomes impossible. The Hubble flow also helps define the large-scale structure of the universe by providing a background expansion against which gravitational systems evolve. Galaxies are carried apart by this flow unless local gravity is strong enough to resist it. This creates a layered structure where bound systems remain intact, while unbound systems drift apart, increasing separation across cosmic time. Redshift measurements across different distances reveal how the expansion rate has changed throughout history. Light from more distant galaxies carries information from earlier times, showing that expansion was once slower and has since accelerated. This provides evidence for the influence of dark energy and helps reconstruct the timeline of cosmic evolution. Despite its smooth appearance on large scales, the Hubble flow is built upon a universe that is highly structured on smaller scales. Galaxies, clusters, and filaments exist within this expanding framework, each responding differently depending on the balance between gravity and expansion. The result is a universe where local stability coexists with large-scale separation. The effect of this flow over billions of years is profound. Distances between unbound galaxies increase continuously, and regions that were once relatively close become isolated. This gradual separation shapes the overall experience of cosmic distance, transforming the universe into a structure where emptiness grows more dominant with scale and time. The Hubble flow therefore represents not just motion, but the fundamental behavior of space itself on the larger scales. It is the mechanism through which expansion becomes visible, measurable, and inevitable in its influence on cosmic separation. As light travels across the universe, its properties are gradually transformed by the expanding fabric of space, producing an effect known as cosmological redshift. This shift is not caused by changes in the light source itself, but by the continuous stretching of space through which the light moves. Each wavelength of light becomes longer as the distance between points in space increases during its journey, slowly altering its energy and color. Over immense distances, this process becomes one of the most important tools for understanding the scale and history of the universe. Redshift provides a direct connection between distance and time. The farther a galaxy is, the longer its light has traveled, and the more its wavelength has been stretched. This means that observing distant galaxies is also observing the universe in its earlier stages. The light carries information from a time when galaxies were closer together and the universe was denser. As this light arrives after billions of years, it reveals how expansion has changed cosmic structure over time. The stretching of light affects all wavelengths, not just visible light. Ultraviolet light can be shifted into visible light into infrared, and in extreme cases even into radio wavelengths. This continuous transformation ensures that distant regions of the universe appear progressively dimmer and redder as their light travels across expanding space. The longer the distance, the more pronounced this effect becomes. This redshifting process contributes directly to the increasing sense of separation between galaxies. As light becomes more stretched, it carries less energy, making distant galaxies harder to observe. Over extremely large distances, galaxies may become effectively invisible to certain observational methods, not because they no longer exist, but because their light has been stretched beyond detectable ranges. The degree of redshift is closely related to the expansion history of the universe. By measuring how much light has been stretched, it is possible to infer how much space has expanded since that light was emitted. This allows astronomers to reconstruct the large-scale evolution of cosmic expansion and understand how galaxies have moved apart over time due to the stretching of space. In regions where galaxies are relatively close, redshift is small and subtle. The effects of expansion are present but not dominant. However, as distance increases, redshift grows stronger, reflecting the cumulative effect of billions of years of expansion. This gradual increase creates a smooth transition from local cosmic environments to the most distant observable regions of space. Redshift also affects the perceived brightness of galaxies. As light is stretched, its energy decreases and fewer photons reach an observer with sufficient energy to be detected in certain wavelengths. This dimming effect compounds the challenge of observing distant galaxies, adding to the impression of increasing emptiness at large scales. Even when galaxies are present, their light may be so weakened that it becomes difficult to distinguish from the cosmic background. The interaction between redshift and cosmic expansion creates a form of observational boundary. At extreme distances, galaxies become so redshifted that their light shifts beyond practical detection limits. This contributes to the cosmic horizon, a limit defined not by physical walls, but by the ability of light to reach an observer in a usable form. Beyond this horizon, regions of the universe may still exist, but their light is no longer accessible. The study of redshift has revealed that the universe is not static but dynamically evolving. Early observations showed that distant galaxies are receding, and further measurements confirmed that this recession increases with distance. This pattern is consistent across the observable universe, reinforcing the idea that space itself is expanding uniformly on large scales. Within local gravitational systems, redshift is minimal. Galaxies bound within clusters or groups do not experience significant internal redshift effects from expansion. Their internal motions and gravitational interactions dominate over cosmic expansion, maintaining stability. However, when viewed from outside these systems, their collective motion within the Hubble flow becomes apparent through their redshifted light. The progressive nature of redshift emphasizes the growing isolation of distant regions. As light travels across expanding space, it becomes increasingly altered, carrying less direct information about its source. This transformation means that the farther one looks into the universe, the more indirect and faint the connection becomes between observer and distant structure. Over cosmic timescales, this process leads to a universe where distant galaxies fade not suddenly, but gradually, their light stretching beyond recognition. This slow fading contributes to the long-term evolution of cosmic visibility, where only nearby or gravitationally bound structures remain clearly observable. Redshift therefore acts as both a measurement tool and a reflection of cosmic expansion. It encodes the history of separation between galaxies into the light itself, showing how space has grown over time. Through this mechanism, the universe reveals its expanding nature not through motion alone, but through the transformation of light across unimaginable distances. At the limit of what can be observed, the universe presents a boundary known as the cosmic horizon, a region defined not by a physical edge, but by the constraints of light and time. This horizon marks the farthest distance from which light has had enough time to reach a given observer since the beginning of cosmic expansion. Beyond this boundary, regions of the universe may exist, but their light has not yet arrived, or may never arrive due to the continuing expansion of space. The cosmic horizon is shaped by the finite age of the universe and the continuous expansion of space itself. As the universe evolves, this horizon changes, allowing new regions to become visible, while others move beyond reach. This dynamic boundary reflects the fact that observation in cosmology is always tied to the travel time of light, which is limited and affected by the stretching of space. Inside the horizon, the universe appears structured and filled with galaxies, clusters, and filaments arranged in a complex network. Outside the horizon, there is no direct observational access. The separation between these regions is not a physical wall, but a temporal and spatial limit defined by the interaction between light speed and expansion. This creates a layered view of the universe, where visibility is constrained by distance and cosmic history. As space expands, the cosmic horizon does not remain fixed. In certain models of accelerated expansion driven by dark energy, the horizon can evolve in such a way that some regions currently visible may eventually cross beyond it. When this happens, light emitted from those regions after a certain point will never reach the observer, effectively isolating those galaxies from future observation. The concept of a horizon introduces a deep sense of separation in the universe. It means that there are regions of existence that are fundamentally disconnected from one another, not because they are absent, but because information cannot travel between them. This limitation transforms distance into a barrier of time where separation is measured not only in space, but in the inability to exchange signals. Within the observable universe, the distribution of galaxies reflects this boundary. Distant galaxies appear as they were in the past, their light carrying information from early cosmic history. Closer galaxies represent more recent states of evolution. The horizon therefore acts as a window into different epochs, allowing observation of cosmic time layered across distance. The further an observer looks, the closer they approach this boundary. At extreme distances, galaxies appear faint, heavily redshifted, and increasingly difficult to detect. Their light is stretched across vast wavelengths, and their signals weaken as they approach the limits of observability. This gradual fading contributes to the sense of increasing emptiness in the universe at large scales. The cosmic horizon is also influenced by the acceleration of expansion. As expansion speeds up, the rate at which distant regions move away increases, affecting whether their light can ever reach an observer. In an accelerating universe, more regions become effectively unreachable over time, reinforcing the long-term isolation of cosmic structures. Despite its name, the horizon is not a single fixed surface. It can be described in different ways depending on how cosmic time is measured and how expansion is modelled. One definition is based on the particle horizon, which describes the maximum distance from which light has had time to reach an observer since the beginning of the universe. Another is the event horizon, which describes the boundary beyond which events will never be observable in the future due to expansion. These horizons define different aspects of cosmic separation. The particle horizon reflects what is currently visible, while the event horizon reflects what will remain permanently observable. Together they illustrate how the universe is structured not only in space but also in time-limited connectivity. Inside these boundaries, the universe remains connected through light and gravitational influence on local scales. Outside them, regions become increasingly detached, unable to exchange information. This separation grows over time as expansion continues, reinforcing the idea that distance in the universe is not only spatial but also informational. The existence of horizons emphasizes that the universe is not fully accessible from any single point of observation. Each region has its own observable limit shaped by the finite speed of light and the evolving expansion of space. This means that the universe as a whole is larger than what can ever be directly observed from any location. As a result, the cosmic horizon contributes to the profound sense of scale in the universe. It defines a boundary of perception beyond which separation becomes absolute in practical terms. Even though these regions may still exist, they are effectively isolated from the observable realm. This increasing separation reinforces the central theme of cosmic distance. The universe is not only expanding in physical terms, but also in the limits of connection between regions. The horizon represents the point where distance becomes indistinguishable from permanent isolation, shaped by the finite speed of light and the accelerating growth of space. On scales larger than individual clusters and filaments, the universe appears as a structure where motion and distance are governed not only by gravity, but by the collective influence of cosmic expansion across immense regions. Within this framework, galaxies do not simply move through space independently. Instead, their large-scale separation is shaped by the continuous stretching of space itself. This creates a background environment in which even stable structures are carried apart over time when they are not gravitationally bound. The relationship between distance and motion becomes especially clear when considering how isolated galaxies behave beyond their local environments. Once outside the gravitational influence of clusters or groups, galaxies follow the general expansion of the universe. Their separation from other galaxies increases steadily not because of active propulsion, but because the space between them grows. This produces a slow and persistent drift that becomes more pronounced as distance increases. Within this expanding framework, the concept of isolation becomes central. Galaxies that are not bound to one another gradually lose interaction over time. The probability of close encounters decreases as separation increases, and the large-scale structure becomes more static in terms of interactions. Although galaxies continue to evolve internally through star formation and stellar processes, their interactions with distant systems diminish as expansion dominates. At intermediate scales, the universe still contains recognizable patterns of structure. Filaments connect clusters, and clusters contain multiple galaxies interacting through gravity. However, between these structures, the distances are vast enough that interaction becomes rare. This creates a patchwork of connected regions separated by large expanses of low-density space, reinforcing the impression of increasing separation at every level of scale. The flow of galaxies within this structure is not random but guided by the underlying gravitational landscape. Matter tends to move along filaments toward denser regions, while empty regions expand and become more pronounced. Over time, this results in a redistribution of matter, where dense regions become more concentrated and empty regions grow larger. This dynamic continues even as overall expansion increases separation between all unbound structures. In this context, the concept of a gravitationally bound system becomes crucial. A bound system is one in which internal gravitational forces are strong enough to overcome expansion. Within such systems, galaxies or stars remain stable relative to one another. However, beyond these systems, expansion takes over and separation increases steadily. This division between bound and unbound regions defines the large-scale architecture of the universe. As time progresses, the distinction between connected and isolated regions becomes more pronounced. Bound systems remain intact, but their separation from other bound systems increases. This leads to a universe composed of islands of structure surrounded by increasingly empty space. Each island evolves largely independently with limited or no interaction with others beyond its local region. The increasing distance between these regions also affects the flow of information across the universe. Signals that once could travel between nearby systems become stretched, weakened, and eventually unreachable as expansion continues. This means that communication between distant regions becomes progressively more difficult, reinforcing isolation, not only in physical terms, but also in informational terms. On the largest scales, the universe approaches a state where structure is preserved locally, but disconnected globally. Galaxy clusters remain intact, galaxies within clusters continue to evolve, and stars within galaxies maintain their orbits. However, the space between these structures continues to grow, reducing the likelihood of interaction over cosmic time. This separation is not sudden but gradual, occurring over billions of years. It reflects the cumulative effect of expansion, acting on all unbound regions of space. Even though local systems remain stable, their relative positions shift over time due to the stretching of space. This slow divergence shapes the overall experience of cosmic distance. The universe at this scale can be understood as a hierarchy of connected systems embedded within expanding space. Each level of structure, from galaxies to clusters, maintains internal coherence, while simultaneously drifting apart from other systems. This dual behavior defines the nature of cosmic evolution on large scales. Ultimately, the large-scale flow of galaxies illustrates a universe where distance is not fixed, but continuously increasing between unbound regions. This persistent separation reinforces the fundamental characteristic of cosmic structure, the dominance of expansion over connectivity at the largest scales, leading to a universe that becomes increasingly isolated as it evolves. Within the large-scale structure of the universe, galaxy clusters represent the strongest examples of gravitational binding forming regions, where matter remains coherently organized despite the continuous expansion of space. These clusters contain hundreds or even thousands of galaxies held together by mutual gravitational attraction and by the dominant presence of dark matter. The dark matter forms an invisible gravitational framework that shapes the motion of visible galaxies, ensuring that the cluster remains stable over long cosmic timescales. Inside a cluster, galaxies move through shared gravitational fields, orbiting around a central region defined by the overall mass distribution. These motions are complex and slow when viewed on human timescales, yet over millions of years they contribute to the gradual evolution of the cluster's internal structure. Galaxies may pass near each other, interact gravitationally, or even merge, forming larger and more massive systems. Despite this activity, the cluster remains a bound system resistant to the large-scale expansion of the universe. The space between galaxies within a cluster is not empty in a strict sense. It contains the intracluster medium, a hot and diffuse plasma, composed primarily of ionized hydrogen and helium. This gas is heated to extremely high temperatures by gravitational processes reaching conditions where it emits X-rays detectable by space-based observatories. Although extremely thin compared to any material on Earth, this medium represents a significant fraction of the baryonic matter within clusters. The presence of this hot gas reveals the energetic nature of clusters. As galaxies move through the intracluster medium, they experience resistance and exchange energy with their surroundings. Over time, this can influence star formation within galaxies as gas is stripped or redistributed through gravitational interactions and pressure effects. These processes contribute to the gradual evolution of galaxies within the cluster environment. Despite the stability of clusters, their boundaries are not sharply defined. The transition from cluster to intercluster space is gradual with decreasing galaxy density, marking the shift from bound to unbound regions. Beyond the cluster, galaxies become increasingly isolated, and the influence of the cluster's gravity weakens. At these distances, cosmic expansion begins to dominate the separation between structures. Clusters themselves are embedded within larger structures known as superclusters and filaments, which form part of the cosmic web. These larger structures are often only partially gravitationally bound, meaning that not all components will remain connected over time. Some regions within superclusters are slowly drifting apart even while clusters within them remain intact. This layered structure highlights the complexity of cosmic organization, where different scales behave differently under the combined influence of gravity and expansion. The dark matter halo surrounding a cluster extends far beyond the visible galaxies and gas. This halo defines the true gravitational boundary of the cluster and plays a central role in maintaining its structure. Observations of galaxy motions within clusters reveal that visible matter alone is insufficient to account for the observed gravitational effects, confirming the presence of this unseen mass. The halo acts as the anchor that stabilizes the cluster against internal and external forces. As time progresses, clusters continue to evolve through internal processes while gradually separating from other clusters. Although they remain stable internally, their position relative to other large structures changes due to the expansion of space. This leads to an increasing isolation of clusters on cosmic scales where each becomes a relatively independent system, surrounded by expanding emptiness. Within this environment, the concept of cosmic distance becomes particularly pronounced. The separation between clusters grows over time not because of motion through space, but because of the expansion of space itself. This effect reinforces the impression that the universe is becoming more empty on large scales, even though matter remains concentrated within bound systems. The evolution of clusters is therefore shaped by a balance between internal gravitational cohesion and external expansion. Gravity maintains structure within the cluster, while expansion increases separation between clusters. This dual influence defines the intermediate scale of cosmic structure, where both forces are significant but operate in different domains. On the larger scales, clusters appear as isolated islands of matter within an expanding sea of space. Each cluster contains its own internal dynamics, yet remains separated from others by vast distances that continue to grow over time. This separation contributes to the overall architecture of the universe, where structure becomes increasingly localized and isolation becomes more pronounced. The study of clusters reveals how matter is organized into stable systems within a universe that is continuously expanding. It shows that while local order can persist, global connectivity decreases over time. This leads to a cosmos where structure survives, but interaction between structures becomes increasingly rare as distances grow. Within the environment of a single galaxy cluster and its surrounding gravitational domain, the distribution of matter begins to transition from tightly bound systems into more loosely connected structures. This region is not sharply separated from intercluster space. but instead forms a gradual boundary where gravitational influence weakens and cosmic expansion becomes increasingly significant. The outer regions of a cluster often blend into faint extensions of filaments, where galaxies are more sparsely distributed and interactions become less frequent. As one moves away from the central regions of a cluster, the density of galaxies decreases steadily. The gravitational pull of the cluster weakens with distance, allowing galaxies at the outskirts to become more influenced by the large-scale expansion of the universe. These outer galaxies may still be temporarily bound, but over long timescales they can drift away from the cluster's gravitational hold, becoming part of the surrounding intergalactic environment. The transition from cluster interior to surrounding space is defined not by a strict boundary, but by a gradual decline in density and gravitational dominance. Within this transitional zone, galaxies may follow complex trajectories influenced by both the cluster's gravity and the expansion of space. Some remain on long, slow orbits, while others begin to participate more fully in the general outward flow of cosmic expansion. Beyond the cluster boundary, galaxies become part of the field population existing in relative isolation compared to those within clusters. These galaxies are not part of dense gravitational systems, and therefore evolve under different conditions. Without frequent interactions or mergers, their structures change more slowly, and their internal evolution is governed primarily by their own gravitational and stellar processes. The space between these isolated galaxies is dominated by extremely low-density gas remnants of the intergalactic medium that fill the universe on large scales. This gas is so diffuse that direct interactions between particles are rare, yet it still traces the underlying dark matter structure. Even in these sparse regions, gravity continues to shape the large-scale flow of matter, guiding it along faint filaments that connect distant structures. As cosmic expansion continues, the separation between isolated galaxies increases steadily. This process is gradual but persistent, leading to a universe where galaxies outside clusters become increasingly distant from one another. Over extremely long timescales, many of these galaxies may move beyond each other's observable reach, reinforcing the sense of cosmic isolation. The role of dark matter remains significant even in these outer regions. Although invisible, its gravitational influence defines the large-scale structure of space, determining how matter is distributed even where visible galaxies are rare. The faint network of dark matter filaments continues to guide the motion of baryonic matter, maintaining a subtle coherence across vast distances. Within this expanding framework, the concept of connectivity becomes increasingly limited. While galaxies may still exist within the same large-scale structure, their ability to interact diminishes as separation grows. Light travelling between them takes increasingly long periods, and the effects of expansion stretch and weaken signals over time. This leads to a universe where local structure remains intact, but large-scale interaction becomes rare. Galaxies within clusters may still interact frequently, but those outside clusters exist in a more isolated state. The further one moves from dense regions, the more pronounced this isolation becomes, reflecting the influence of expansion on cosmic structure. The outer regions of clusters therefore serve as a transitional environment between highly structured systems and the vast emptiness of intergalactic space. They illustrate the gradual nature of cosmic separation, where boundaries are defined by changing densities rather than sharp divisions. This continuity emphasizes that the universe evolves smoothly, with no abrupt transitions between structure and emptiness. As time progresses, the distinction between cluster-bound and unbound galaxies becomes more pronounced. Bound systems remain intact, while unbound systems drift further apart. This divergence shapes the long-term evolution of cosmic structure, reinforcing the trend toward increasing separation across all large scales. The outer cluster environment thus represents a key stage in the broader pattern of cosmic evolution, where gravity and expansion compete to define the structure of space. It highlights how even within regions of relative density, the influence of expansion gradually increases with distance, leading to a universe where isolation becomes the dominant feature at large scales. Within the extended environment surrounding a galaxy cluster, the Milky Way resides in a region that reflects both local gravitational stability and broader cosmic isolation. This region is part of a small gravitationally bound group of galaxies known as the Local Group, which includes the Milky Way, the Andromeda Galaxy, and several smaller satellite galaxies. These systems are held together by mutual gravitational attraction, forming a compact structure embedded within the much larger framework of the cosmic web. Inside this local system, galaxies interact through gravity over long timescales. The Milky Way and Andromeda galaxies, for example, are slowly moving toward each other due to their mutual attraction, indicating that local gravity can overcome cosmic expansion at this scale. Smaller satellite galaxies orbit larger ones influenced by complex gravitational interactions that shape their structure and evolution. Despite these interactions, the local group remains isolated from other galaxy groups by vast distances of intergalactic space. The space surrounding the local group is extremely sparse, containing only thin traces of gas and isolated galaxies. This region is part of the larger intergalactic environment, where matter is distributed in a highly diffuse state. The density of matter here is so low that interactions between galaxies are rare, and most galaxies evolve without significant external influence. This isolation contributes to the gradual divergence of structures over cosmic time. Beyond the local group lies the outer regions of the Milky Way's gravitational influence, often described as the galaxy's extended halo environment. This halo includes faint streams of stars and dark matter that extend far beyond the visible disk of the galaxy. These structures are remnants of past interactions and mergers preserved in the outer regions, where gravitational forces are weaker but still significant. The Milky Way itself is embedded within a larger halo of dark matter, which extends far beyond the visible boundaries of the galaxy. This halo provides the gravitational framework that holds the galaxy together and influences the motion of stars within it. Observations of stellar motion in the outer regions of the galaxy reveal the presence of this invisible mass, which dominates the galaxy's total mass budget and ensures its long-term stability. As one moves farther from the Milky Way, the density of matter decreases sharply. The transition from the galactic halo to intergalactic space is gradual with no clear boundary. Stars become increasingly rare, and the space between them becomes dominated by extremely low-density gas and dark matter. This region represents the interface between the galaxy and the broader cosmic environment. Within this extended region, the influence of the cosmic web becomes more apparent. The Milky Way is connected to other structures through faint filaments of gas and dark matter, which guide the large-scale distribution of matter. These filaments form part of the larger network that connects galaxies across vast distances, although the connections are extremely tenuous at this scale. Despite these connections, the Milky Way and its local environment remain largely isolated from other galaxy systems. The nearest large galaxy, Andromeda, is separated by a distance of millions of light-years, and even closer dwarf galaxies are still separated by vast regions of near-empty space. This separation emphasizes the dominance of distance at cosmic scales, where even nearby structures are separated by incomprehensible gaps. The motion of galaxies within the local group is governed primarily by gravity rather than cosmic expansion. This allows the system to remain coherent over long periods of time. However, beyond the local group, expansion becomes more significant, leading to increasing separation between galaxy groups. This creates a layered structure in which local systems remain bound, while larger scales become progressively more isolated. The Milky Way's position within this structure highlights the balance between connection and isolation. It exists within a small gravitationally bound system, while simultaneously being separated from other systems by vast cosmic distances. This dual state reflects the broader nature of the universe where local stability coexists with large-scale separation. Over time, the local group will evolve internally through interactions between its member galaxies, while its separation from other groups continues to increase. This long-term divergence contributes to the overall trend of increasing isolation in the universe, where galaxies become more separated as cosmic expansion continues to dominate large-scale structure. The region surrounding the Milky Way therefore serves as a clear example of how cosmic distance operates across multiple scales. It shows how local gravitational systems remain intact, while still existing within a universe that is expanding and becoming increasingly empty on larger scales. Within the extended halo environment surrounding the Milky Way, the structure of space becomes increasingly diffuse, marking a transition between the dense interior of a galaxy and the vast emptiness of intergalactic space. This halo is composed of both dark matter and faint streams of stars that trace the remnants of ancient galactic interactions. These stellar streams are the result of smaller galaxies being gradually disrupted and absorbed by the Milky Way's gravitational field, leaving behind elongated trails of material that slowly disperse over time. Tonight, the story begins with the distance so vast that the human mind struggles to hold it. The nearest galaxy beyond our own lies millions of light years away, separated not by mountains, oceans, or empty deserts, but by an abyss of space so enormous that even light takes ages to cross it. Between galaxies, there are regions where a traveller could move for millions of years without passing a single star. Entire civilizations, if they exist, may be trapped forever on opposite sides of these cosmic voids, separated by distances that grow larger every second as the universe expands. In this journey, Cosmic Bedtime Stories explores the hidden reality of intergalactic space, the unimaginable scale of the cosmic web, and why the distances between galaxies may be far more unsettling than the galaxies themselves. If relaxing journeys through the universe help with sleep study or quiet reflection, please take a moment to like this video, subscribe to the channel, and join us for more peaceful explorations of the cosmos. Now, as the stars drift silently across the darkness, the true scale of the universe begins to reveal itself. The dark matter halo extends far beyond the visible disk of the galaxy, forming a vast spherical region that dominates the Milky Way's total mass. Although invisible, this halo determines the motion of stars in the outer regions of the galaxy, ensuring that they remain gravitationally bound despite their distance from the galactic center. Its influence is inferred through the rotation curves of galaxies, which show that visible matter alone cannot account for the observed motion of stars. As distance increases within the halo, the density of visible matter decreases rapidly. Stars become sparse, and the space between them grows increasingly empty. This region is not a sharp boundary, but a gradual fading of structure, where the galaxy transitions into the surrounding intergalactic medium. The remaining gas in this region is extremely thin, composed mostly of ionized hydrogen that exists at densities far below any terrestrial vacuum. Beyond the halo lies intergalactic space, where galaxies are separated by distances measured in millions of light years. In this region, the cosmic web becomes the dominant structural feature, with faint filaments of gas and dark matter connecting distant galaxy systems. These filaments are extremely diffuse, yet they play a critical role in guiding the large-scale distribution of matter across the universe. Within these filaments, matter flows slowly toward denser regions driven by gravitational attraction over long timescales. This movement is not rapid or turbulent, but occurs as a gradual drift of gas and galaxies along the underlying structure of dark matter. Over billions of years, this process contributes to the formation and evolution of galaxy clusters, while surrounding voids become increasingly empty. The transition from filament to void is marked by a steady decline in density. In void regions, galaxies are rare and widely separated, and the intergalactic medium becomes even more tenuous. These regions represent some of the most empty environments in the universe, where matter is so sparsely distributed that interactions between particles are exceedingly rare. Despite this emptiness, the influence of dark matter remains present. Even in voids, dark matter defines the gravitational landscape, shaping the faint structure of space and guiding the distribution of the sparse matter that remains. Its presence ensures that the universe retains a connected structure on the largest scales, even as visible matter becomes increasingly isolated. The expansion of space further enhances this separation. As the universe expands, the distance between galaxies and filaments increases, gradually stretching the cosmic web. This process does not destroy structure, but increases the scale of separation between its components, making the universe appear more empty over time. In this environment, galaxies outside clusters exist in relative isolation. They are no longer strongly influenced by nearby systems and evolve primarily through internal processes. Star formation, stellar evolution, and internal dynamics continue, but external interactions become rare. This isolation contributes to the diversity of galactic structures observed in different environments. The Milky Way's position within this larger framework reflects a balance between local coherence and cosmic isolation. While it remains part of a gravitationally bound group, it is also embedded within a universe where most regions are separated by vast distances. This duality highlights the layered nature of cosmic structure, where small-scale stability exists within large-scale separation. Over time, the separation between galaxies, clusters, and filaments continues to increase due to cosmic expansion. This leads to a gradual reduction in interaction between distant systems, reinforcing the sense that the universe is becoming more isolated on large scales. The structure remains, but the connections between its parts weaken as distance grows. The halo and surrounding intergalactic regions therefore represent a transitional domain in cosmic structure, where galaxies shift from being part of dense environments to existing in increasingly empty space. This transition illustrates the continuous nature of cosmic separation, where no sharp boundaries exist, only gradual changes in density and interaction. On the smallest scale within the cosmic hierarchy of structure, the solar system occupies a region that appears stable and self-contained, yet it is still embedded within the larger environment of the Milky Way galaxy. The gravitational influence of the Sun dominates this region, binding planets, moons, asteroids, and smaller bodies into coherent orbits. These orbits are maintained by the balance between gravitational attraction and orbital motion, creating a stable system that persists over billions of years. Within this system, distances are vast compared to human experience, but negligible on galactic scales. The space between planets is mostly empty, with only thin distributions of dust-charged particles and solar wind filling the interplanetary medium. This medium is shaped by the Sun's activity extending outward as a continuous flow of charged particles that defines the heliosphere, a protective bubble surrounding the solar system. Beyond the heliosphere lies interstellar space, where the influence of the Sun weakens, and the broader structure of the Milky Way becomes more apparent. Even here, space is not truly empty. It contains extremely low-density gas cosmic rays and magnetic fields that extend across the galaxy. These elements form part of the interstellar medium, which connects the solar system to the larger galactic environment. The motion of the solar system through the Milky Way is governed by the galaxy's overall gravitational field. It orbits the galactic center over extremely long timescales, moving through spiral arms and regions of varying density. Despite this motion, the solar system remains gravitationally bound, maintaining its internal structure, while participating in the broader dynamics of the galaxy. As distance increases from the solar system, the density of matter changes gradually. Nearby stars are separated by many trillions of kilometers, and even the closest stellar neighbors exist in a state of near-complete isolation compared to planetary systems. These vast separations define the scale of interstellar space, where interactions between star systems are extremely rare. Beyond the immediate galactic environment, the structure of the universe becomes dominated by the same patterns seen on larger scales: clusters, filaments, and voids. The Milky Way itself is part of a larger gravitationally bound group, and beyond that it participates in the cosmic web. However, at the scale of the solar system, these larger structures are not directly visible, even though they define the overall environment in which the system exists. The extreme emptiness between stars and galaxies emphasizes the central theme of cosmic distance. Even though matter is organized into structured systems at multiple scales, the majority of space remains nearly empty. This emptiness becomes more pronounced as one moves outward from planetary systems to galactic and intergalactic scales. Light traveling from distant stars or galaxies carries information across these vast distances, but the journey is slow on cosmic timescales. Each photon moves through regions of space that are largely devoid of matter, influenced primarily by the expansion of the universe over the largest distances. This creates a connection between local systems and the distant universe that is defined by time delay and gradual signal transformation. The solar system itself is not isolated in an absolute sense, but it exists within a hierarchy of increasingly larger structures, each separated by greater distances. From planets to stars, from stars to galaxies, and from galaxies to clusters, the pattern of increasing separation remains consistent. This hierarchy reflects the fundamental nature of cosmic structure, where local order coexists with vast emptiness. At the larger scale, the universe is dominated by separation. Galaxies are divided by immense distances, clusters are isolated within expanding space, and voids occupy most of the volume of the cosmos. The solar system, while stable and coherent on its own scale, is part of this broader structure where distance continuously increases between unbound regions. The overall result is a universe defined not by proximity but by separation. Structures exist at every level, but they are embedded within an expanding framework that increases the distance between them over time. This creates a cosmic environment where isolation is not an exception but a fundamental feature of large-scale existence. The final perspective reveals a universe that is both structured and profoundly empty. Matter is organized into systems of increasing scale, yet the space between those systems dominates the total volume. This imbalance between structure and emptiness defines the true nature of cosmic distance, where separation itself becomes the most fundamental characteristic of the universe.